superposition, and standing waves. In this session, we will explore the fundamental behaviors of waves when they encounter one another. We will begin with the principle of superposition and distinguish between linear and nonlinear waves. From there, we will examine the specific outcomes of wave interaction, known as constructive and destructive interference. We will also apply these concepts to sinusoidal waves and look at the formal analysis model used to describe waves in interference. A defining characteristic that separates waves from particles is their ability to occupy the same location in space simultaneously. When two or more traveling waves move through a medium, they combine according to the superposition principle. This principle states that the resulting wave function at any point is simply the algebraic sum of the individual wave functions. Mathematically, we can say the total displacement y equals the sum of the individual displacements, y1 plus y2. Waves that follow this additive rule are referred to as linear waves. Linear waves are typically identified by having amplitudes that are much smaller than their wavelengths. In contrast, nonlinear waves have large amplitudes that violate the superposition principle. An important result of this principle for linear waves is that traveling waves can pass directly through each other without being permanently changed. Just like ripples on a pond, the individual pulses maintain their original shapes and properties after they have moved past the point of intersection. Constructive interference occurs when the displacements of two pulses are in the same direction. The slide shows a sequence of two pulses, y1 and y2, moving toward each other. In the second image, they begin to overlap, and the total wave function becomes the sum of the two. With the crests perfectly aligned, the resulting complex wave reaches a maximum amplitude that is larger than either of the individual pulses. Once the interaction is over, as seen in the final image, the pulses continue on their original paths with their shapes completely unchanged. Destructive interference happens when the displacements of two pulses are in opposite directions. In this case, one pulse, y2, is inverted relative to the first pulse, y1, meaning its displacement value is negative. As these pulses overlap, the amplitude of the combined wave becomes less than that of the individual waves because the positive and negative values partially or fully cancel each other out. This demonstrates that interference is a process of combination rather than a permanent physical collision. When we consider the superposition of two sinusoidal waves with the same frequency, wavelength, and amplitude, but differing by a phase constant, we use trigonometric identities to find the result. If the first wave is represented by the amplitude a times the sine of kx minus omega t, and the second wave includes a phase shift phi, the combined wave remains sinusoidal with the same frequency and wavelength. The new resultant amplitude is calculated as 2 times the original amplitude a, multiplied by the cosine of half the phase constant. The specific outcomes of sinusoidal interference depend on the phase constant. Constructive interference occurs when the phase difference is 0 or an even multiple of pi radians, such as 2 pi or 4 pi. In this state, the waves are said to be in phase, and the resulting amplitude is twice the original amplitude. Destructive interference occurs when the phase difference is pi radians, or any odd multiple of pi. Here, the waves are 180 degrees out of phase, and the resulting amplitude is 0, as the waves perfectly cancel each other. This slide provides a visual comparison of different interference states. In the top graph, where the phase difference is 0 degrees, the blue and green individual waves are in phase and indistinguishable, resulting in a larger red-brown wave. The middle graph shows the waves 180 degrees out of phase, where the crest of one aligns with the trough of the other, leading to total cancellation. The bottom graph illustrates an intermediate result with a phase shift of 60 degrees, where the interference is neither fully constructive nor fully destructive. An acoustical interference device can demonstrate these principles using sound. Sound from A speaker enters A tube and splits into two paths at point P. These paths have lengths designated as R1 and R2. The difference between these path lengths, known as delta R, creates a phase difference between the waves when they recombine. If the path difference is an integer multiple of the wavelength, we hear constructive interference. If the path difference is an odd half multiple of the wavelength, destructive interference occurs, and the sound is minimized. Let us look at a practical example involving two speakers separated by 3 meters and driven by the same oscillator. A listener moves from a central point to a new position point P, which is 0.350 meters away, where they hear the first minimum in sound. This minimum indicates that the path difference equals half a wavelength. By using the Pythagorean theorem, we calculate the path lengths from each speaker to the listener as 8.08 meters and 8.21 meters. The difference of 0.13 meters tells us the wavelength is 0.26 meters. Using the speed of sound, 343 meters per second, we find the oscillator frequency is 1.3 kilohertz. In summary, the superpositional principle explains how waves combine algebraically when they occupy the same space. Linear waves are unique because they do not permanently alter each other's shapes after an interaction. We have learned that constructive interference results from waves being in phase, while destructive interference happens when they are 180 degrees out of phase. Finally, we touched on the concept of quantization, which occurs when waves are confined within systems that have specific boundary conditions. To wrap up, consider the difference between the word interfere, as used in sports, versus its meaning in physics. In physics, it refers to the combination of waves without permanent change. Think about what happens to the resulting amplitude if two identical waves are shifted by a phase constant of pi. Use the superposition principle to explain why the waves would cancel each other out in that scenario. This concludes our look at the analysis model for waves in interference.